Time for us to do some practice problems involving functions of multivariables. And we're just starting out very simple, focusing a little bit on things like what's our domain, what do we mean when we talk about level curves and level surfaces, because we're kind of easing our way into our new topic of multivariable calculus. Of course, that doesn't mean we can take it easy. We got to make sure we do the practice. The more we practice, the better we get. And we want to be so wonderful. We want people to be like, wow, look at them. They know calculus. They're awesome. I want to hang out with those people. That's our goal, right? And we get there by practice. So if you're following along with the video, make use of the pause button. See a problem? Pause it and try it yourself first and see how far you get. And if you ever do need my help, I'm there. You just unpause me. And together, our powers combined, we'll be able to figure it out. Well, let's begin. So our very first problem, this is just really a warm-up, right? So suppose you have a function f of xy equal x squared plus 2y squared. Find the following. So let's think about what this means. So this says, look, our function has two inputs, x and a y. And so in other words, we plug two values in, and it says take whatever is called x becomes x squared, whatever is y becomes y squared. Now, be careful that you don't tie too much to the symbols. And so we'll get into that as we go down our list. But some of these are pretty straightforward. So if I plug in 0, 2, okay, that says x equals 0, y equals 2. So it would be 0 squared plus 2 times 2 squared. And of course, we can simplify that. That becomes 0 plus 2 times 4, which is 8. Okay, that's not so bad. How bad could it be? F of 1, 1. So now, what does it say? Well, look, it says we're plugging 1 in for x and 1 in for y. So 1 squared plus 2 times 1 squared, that's 1 plus 2. That gives us 3. Okay, T1. Well, what is that? Well, it says now what we're plugging into the X slot is we're plugging in T. And what we're plugging into the Y slot is we're plugging in 1. So that says, okay, replace the X by T. So T squared, and Y we're going to replace by 1. 2 times 1 squared. Or if you like, that becomes T squared plus 2. Okay, that's a little bit more interesting. But of course, we can still get even more interesting. The next one, T plus 1 comma T. Okay, so what's going on here? Well, it says that we're replacing X by T plus 1. So everywhere where we see X becomes a T plus 1. So there's an X there. So that's going to become a T plus 1. And here, we're plugging T into the Y slot. So everywhere there's a Y, it's going to become a T. So 2 times T squared. Well, of course, you can simplify that if you want. That's really T squared plus 2T plus 1 in the first slot, 2T squared in the second slot. So it becomes 3T squared plus 2T plus 1 if you expand and combine. Now, oftentimes, it really makes sense to sort of have this intermediate step. If we just wrote down 3T squared plus 2T plus 1, we'd be like, where did that come from? But because we had the intermediate step, we're like, oh, okay, I see what's going on. Now, this next one might throw you off. Here we have f of x comma y. It's x squared plus 2y squared. What is f of y comma x? You're saying it's the same thing, right? We have variables. It's the same set of variables. Shouldn't it be the same function? And no, it's not. So you got to be careful here. When we talk about a function of x and y, we're just saying, look, these are convenient names here. We could, of course, done other things. So, for example, I could have thought of this as really a function of, I'll put a square here and a triangle. I'm just saying there's something that goes into there, there's something that goes into there. And the rule is whatever goes into there, you're going to square it. Then plus 2, whatever goes into that slot, you're going to square it. Regardless of what the names are, that's what you do. That's what the process says to do. So f of y comma x is not the same as f of x comma y, unless you happen to have a really nice function, but we're probably not going to have that right away. So what does it say? Well, this is, look, it says the first slot is becoming y. Now what we plug into the first slot, it says to square that. So this would be y squared plus 2. And see, now that's the second slot. Second slot is x squared. So you get y squared plus 2x squared. All right, now the last one. What is f of cat comma dog? Now, at this point you're thinking, okay, this is ridiculous. I can't talk about f of cat comma dog. Well, sure we can. We can say, look, because our function is a rule. It says whatever you plug into the first slot, you square that. Whatever you plug in the second slot, you square it and you double, and you add the results. So f of cat comma dog would be f of, take your cat squared plus 2 times the dog squared. And at this point, we really can't do anything else because, well, we don't know what to do for those operations. But that's what it would be. And if we were talking about symbolically, that would be our answer. So just remember, functions they're rules. And so if you have a function with multiple variables, you say, look, there's a rule where there's multiple inputs. And if you change the name of any single input, you just change where it is in the corresponding expression. Make sure you count for everything. And so that's the big takeaway from this problem. Okay, good. Oh, see, that's not so bad. Wow, great. Cats and dogs, life is good. Let's try another problem. Find and sketch the domain of the following function. So we're not sketching the function. That would be a surface up in 3 dimensions. We're sketching the domain, which means we're looking for something in our inputs. So for us, we look at it and say, hey, it's a function of 2 variables, and the variables are called x and y. So our answer is going to be some region in the xy plane. So that's what we're after. What's the appropriate region in the xy plane? Okay, so we say, hey, if it's domain, we have some issues. We have divide by 0. We don't want to do that. We have square root of a negative. We don't want to do that. And then we have a log of anything less than or equal to 0. We don't want to do that. These are our problems. And we don't see anything else that's a problem. There's no crazy trig function or anything. So we say, okay, look, these are the issues. As long as we avoid those problems, life is good. So let's talk about some of these, because I think some are easier than others. So suppose we start with the numerator. It has a square root in it. We say, okay, look, in order for this to be possible, we need to have 2x minus x squared has to be greater than or equal to 0. That's the only way this could possibly work. If 2x minus x squared was negative, I have a square root of a negative, I'm out. Game's over. Okay, so what does that tell us? Well, let's think about 2x minus x squared. Now you can actually see something here. If you multiply this as x times 2 minus x, and so if you think of this as a function, and so I'm going to be a little careful here. So I'm just thinking of this as the function. Here's y, and I want to, here's x. Here's f of x, which is x times 2 minus x. What would it look like? Well, you can see where the intercepts would be. Where does it hit the axis? It hits it at 2 places, at 0 and at 2. So it hits there and there. It's a parabola, and which way does it open? Up or down? Opens down. Negative in front of the x squared. So we see that's what it is. We say, so 2x minus x squared is going to be greater than or equal to 0. That's really telling us that we have to be between 0 and 2, because that's where we're above the axis. That's where the function is positive. But if we go above 2, we're negative. If we go below 0, we're negative. So that's a constraint. All right. So that takes care of square roots of negatives. Let's do our log function. All right. So for our log, what do we need? Well, we need the inside of the log, x minus y squared, has to be positive. Or we could say, look, x has to be above y squared, greater than y squared. Now, of course, it doesn't, what do we mean by above when we're talking about x? Well, if we think about it, what is that? Well, in terms of the coordinate system, if I draw here x and y, x equals y squared. I'm going to do it with a little dotted line. It's a parabola, but it's turned sideways. So, y equals x squared is this parabola. We're turning it sideways, and so we get this form. This is x equals y squared. Now, you just have to think, which side are you on? Well, if I want x to be greater than y squared, it sounds like I should be a larger value, and that's to the right. And that's the correct thing. Now, if you're not sure, it's very easy to figure out. You just pick a point. Like here's a point, x equals 1, y equals 0. And now you say, is it true or false? Is 1 greater than 0 squared? If it's true, you say, good. That's the side we want to be on. So we can say, aha, we have to be inside of that parabola turned sideways. All right, good. We should have probably drawn a picture for our previous one as well. Let's do a quick picture for our previous one. So 0 less than or equal to x less than or equal to 2 says what? Well, you draw x equals 0 and x equals 2, and then you say everything where x is between 0 and 2. So that's this strip right up and down. All right, so now we have two things figured out. We know we've dealt with the square root, we've dealt with the log term, so we're good to go. One more thing to figure out, divide by 0. Now, let's think about it. When would we divide by 0? That would be, when does the log of x minus y squared equal 0? So we need to have natural log of x minus y squared is not 0. Well, okay, so that's what we need. Now, the only time a log of something equals 0 says, hey, that means I need x minus y squared is not 1. All right, or I say, look, x cannot be 1 plus y squared. Well, what is that? Let's look at that graph. X equals 1 plus y squared. Well, that's like taking the graph of x equals y squared, but now we're going to shift it over by 1. So that would be just this graph here. But then we say, look, as long as you're not on that parabola, everything else, it's fair game. And so there we go. That's everything else except that one little curve. All right. Now, how do we get our final answer? What we have to do is we have to say, look, we've taken all of our problems and we've identified them. We can't be on this parabola. We have to be inside of this strip. We have to be to the right of that parabola. And we just lay them all on top of each other. And when we do that, we're going to get one region. And that's the region where all of them are satisfied simultaneously. So it's like we're put everything all on top, stacked together. And so we'll sketch our various curves in that we need to sketch. our dotted ones, well, the x equals y squared. It looks something like that. The x equals 1 plus y squared. It looks similar, just shift it over. It looks something like that. And that's dotted because we don't want to be there. And we have x equals 2. Okay, I'm going to draw that dot as well, but I'm going to go back and visit that. And now we start to say, how does it all fit together? Well, we can include the points on x equals 2. So I'm going to make that solid. Where you have places intersecting, like you'll see I have intersections there, if all of the pieces are saying include, then include. If even one piece says, hey, don't include, then it's a non-include. And the way we mark that, open circle is include, open circle is non-include, closed circle means do include. So these are points where we're not going to include. And then everything else is shaded inside. So we have that part, and we have that part. And there we go. That's our region. We could mark some curves if we wanted to. So for example, we could say this is the curve x equals 1 plus y squared. Over here, this is the curve x equals y squared. And over here is x equals 2. But that's it. Every point inside of that shaded part is in our domain. Everything that's not in that shaded part is out of our domain. And there we go. That's it. That's not so bad. Just check your 3 problem areas. Get rid of all the problems. Life is good. All right. Well, let's do it again. Sketch the domain of the function. And now it's very similar. And we say, okay, look, let's just go through it. We have logs, we have square roots, we have division. So we say, okay, we need to go through our 3 potential problems. So we'll just say we have a potential divide by 0. We'll have to figure that out. We have a square root of something which is negative, and we have a log of something which is less than or equal to 0. Okay, so we just have to go through, piece them together one at a time, and as we do so, we'll get a little bit better understanding of what's going on. Let's start with the numerator. That has a log. Okay, so what do we need? We need the inside part of the log has to be positive. So we need to have y minus x minus 3 squared is a positive value. Another way to say that is that y has to be greater than x minus 3 squared. Okay, well, we can get a good idea of what that is. So x squared, that's our parabola. The x minus 3 on the inside is a shift, and it shifts to the right, so that it would come here at 3. So we now have this nice parabola coming up. And I should have drawn a dotted line because it's a strictly greater than. Retrospect, okay, I'll put a little dash here just to remind myself this is not include. And now we need to be above it. Okay, so we have to be on top of this. Okay, so that's pretty easy to spot which part we have. Normally, if you have a curve, it'll split your plane into 2 parts. You just have to figure out which part do I need. And you do it by testing if you're not sure. But sometimes you can look and say, aha, I see what's going on. No problem. No problem. So that takes care of our log. Our square roots is going to be a little bit more interesting because we actually have 2 of them. So for each square root, we have to think about what happens. And it'll probably be something slightly different. That's not too surprising. So let's see what we have. The first square root says, look, 9 minus y has to be greater than or equal to 0. Okay, well that tells us, if we move the y across, y has to be less than or equal to 9. Oh, that was actually pretty straightforward. Here, 3 minus x. That has to be, again, greater than or equal to 0. Well, what does that tell us? It tells us x has to be less than or equal to 3. So in terms of our sketch, we say, look, here's this line, x equals 3. Here, there's this line, y equals 9. And we want to do what? We want to be below 9 to the right of 3. Sorry, to the left of 3, below 3. So, in terms of our square roots, we want to be in this part right here. All right, so great, beautiful. Okay, well, that takes care of our square roots of negatives. Now, are we done? Not yet. There's one more thing. Our classic divide by 0. We don't want to do it. We don't want to do it. Would not be prudent. It would not be prudent. So, how does that happen? Well, if we were to divide by 0, it would have to be the case that these two would somehow cancel. So, we'd have to have square root of 9 minus y minus square root of 3 minus x equals 0. Let's just sort of follow what that says. So that would say what? Well, move that across. Square root of 9 minus y would have to be the square root of 3 minus x. Okay, well, let's square both sides. If we square both sides, we're looking at places where 9 minus y was equal to 3 minus x. Okay, that's looking promising. Well, let's just sort of move things around. So, for example, let's move this across, and we'll move these other terms around here. So we would get y would be equal to, and here it'd be x plus 6. Okay, good. So y equals x plus 6. Now, that says we have to really, that's where we get a 0 downstairs. So this is, we want to avoid. Okay, so let's keep that in mind. We don't want to be there. Now, where is y equals x plus 6 fit? Let's come back to here. We also have to be, because of the square roots, inside this part. So y equals x plus 6 would be this line there. So that's where we need to avoid. Y equals x plus 6 is out. We don't want that. All right. So what happens when we now take all of these and put them on top of each other? What do we see? Well, we're going to see the following picture. So we'll draw our grid, and we need to mark some lines here. Well, we have this parabola, x minus 3 squared. Now notice it intersects here at 0, 9, which is right there. Ooh, that's very convenient. Okay, so if here is 3, and here we'll put as 9, then we have this parabola coming down, and it's that dotted line. Okay, because I don't need to worry about what happens above 3, I just need to do the left-hand side. And now we're going to have another dotted line that goes through 6, y equals x plus 6. And there's this corner. Now, this corner is an open circle. Why? Because y equals x plus 6 actually goes right through that corner. That would be 0 minus 0. Very zeroy downstairs. Okay, so these corners up here are also open because we're going to have problems. That's when we'd have a log of 0. And, well, dotted line, these are all certainly open. Well, I'll just mark it as open. just to emphasize. But lastly, we say, okay, where do they overlap? And when we do that, we see, aha, here's our picture. And lo and behold, we get our shape. So it's kind of a piece of a parabola, and it's an interesting little curve. Maybe not the most obvious thing, but that's all right. We just work through it patiently, and lo and behold, we get out what we need. And so there we go. There we go. Great. Wonderful. All right, well, let's move on. So let's try something a little different. So here we go. Sketch and label the level curves for the function f of xy equals y over x squared plus 1 for the values -1, -0.5, 0, 0.5, 1. Now, what do we mean by level curves? Well, we're thinking of these are the outputs. So in other words, z equals these values. So we're looking at the heights and saying, let's slice our function. What does it look like? So it's actually not so bad. We say, look, we're just going to set our function equal to each one of these values and simplify and see what we get. So if we start y over x squared plus 1 equals -1, well, that says y equals minus x squared minus 1. Y over x squared plus 1 equals -0.5. That's y equals -0.5 x squared minus 0.5. Y over x squared plus 1 equals 0. Well, that's y equals 0. See, we're clearing our denominators, multiplying across. And you probably can say, wow, I spot a pattern here. I think I can see where we're going. Good. That's what we want. And so we say, all right, these are our level curves. What are they? Well, they're curves in the plane. So those are the actual functions. They're all parabolas of some sort. Okay, great. Well, but now what? Well, now we have to actually draw what the parabolas are. So we'll just mark, here we go, x and y. And what do we have? Well, let's start with the easy one. Y equals x squared plus 1. It's our standard parabola shifted up by 1. So we'll draw that, and let's say here's 1. So there we go. And a half x squared plus half, it's taking our standard parabola and it's squished it down by a factor of a half. But then we've also moved it up by a half. So it's going to be a little bit broader. So it's going to look something like that. Y equals 0. That's pretty easy to sketch. Y equals -0.5 x squared minus a half. Well, that's very similar to this. It's just the negative of it. And minus x squared minus 1. Again, very similar to what we started with before. Just a negative. Now, we're not done yet. We did our sketch, but we also should label. Now, when we talk about labeling, we just say for each curve, there's a value. In other words, what's these numbers here? So, starting with -1, that's this curve, -0.5, 0, 1/2, and 1. And that's our answer. That's not so bad. Actually, level curves tend not to be too bad. We just say, look, set our function equal to a constant, and then draw. It'll either be something which we could draw, or maybe it's kind of hopeless. But, even if it's hopeless, we can still at least talk about the theory. So we'll have some times when we talk about that in future sessions. All right, well, let's do another one like that. That was pretty quick, right? So we can do at least 2 like that. Sketch and label the level curves for the function z is 4y over x squared plus y squared plus 1. Now you notice we don't say f of xy equals, we say z equals. Well, sort of what we're implicitly saying, This is our function of x and y. All right. Well, it should be a little bit more interesting, I suspect. Let's figure it out. So, but it's just, the process is the same. You see, these values here, these are our z values, or if we want to sound fancy, z. And we say, okay, so what do? Well, we simply set our function equal to each one of them and simplify. So 4y over x squared plus y squared plus 1 equals 2. Well, we can move it across. So I'm going to move this across, and I'm going to move the 2 across. In other words, divide by 2. This is the same as saying 2y equals x squared plus y squared plus 1. All right, well, now what? Well, that's really the same as x squared plus y squared minus 2y plus 1 equals 0, right? Yeah, it is. And what is that? Well, that's x squared plus y minus 1 squared equals 0. Well, that's going to be an interesting level curve. We'll get to that one in a minute. Okay, now we'll repeat. Similar process as we go along. How about for 1? Well, 4y over x squared plus y squared plus 1 equals 1. That would give us what? Well, it says 4y equals x squared plus y squared plus 1, because you multiply across. Or you can say, hey, that's really x squared plus y squared minus 4y. And now, what would we need? Because we can kind of see, if you see an x squared, y squared together, it's a circle. So you'd want to say, well, let's complete the square. And if you were to make this a perfect square, y squared minus 4y, you would need to add plus 4. Y plus 4, take the middle term, divide by 2, and square. You might say, okay, but wait, there's really only a plus 1. So that says you've got 3 too many. Well, move and put 3 more on the other side. You can check. See, if you subtract 3, you have a net of plus 1. So what is this? Well, it's x squared plus y minus 2 squared equals 3. Well, okay, that'll be something. All right, keep going. And the next ones aren't so bad. 4y over x squared plus y squared plus 1 equals 0. Well, that's easy. Multiply across, that goes away. 4y equals 0 is just another fancy way of saying y equals 0. Okay, 4y over x squared plus y squared plus 1 equals negative 1. Well, you can see there's not much that's going to change other than the sign. And so it's going to feel very similar to what we did above. So instead of being minus 4y, it becomes plus 4y, but you still do the same, add 4 equals 3. Or x squared plus y plus 2 squared equals 3. And our last one, 4y over x squared plus y squared plus 1 equals minus 2 is the same as minus 2y equals x squared plus y squared plus 1, which becomes the same as x squared plus y squared plus 2y plus 1 equals 0, or x squared plus y plus 1 squared equals 0. All right. So we did the following. We took our function and set each one equal to the outputs that we were interested in. So the outputs were specified, 2, 1, 0, minus 1, minus 2. Now what we're going to do is say, okay, we've rewritten them in a way that we can actually plot them. So our next step is to draw them, and then we have to do the label. So we've sort of done the prep work so that we can now finish the sketch and the label. So if we do this, what's going to happen? Well, we'll get the following. We draw our grid. So let's start with maybe the one in the middle. That's probably the easiest. y equals 0. That's super easy. That's the x-axis. So we say, okay, good. Here we are, y equals 0. And now, let's move up. Let's do 1. X squared plus y minus 2 squared equals 3. Well, that says our center is at 0, 2. So it's a circle. Radius is root 3. Okay, so it's going to be something. Now, square root of 3, it's less than 2. So it's going to be something that looks like this. All right. If you come down here, it's a similar situation, except instead of being at 0, 2, the center, now the center is at 0, minus 2. It's essentially the mirror image. All right. Now, the interesting one. What does x squared plus y minus 1 squared equals 0 look like? Does it look like anything? Okay, that's actually not a trivial question. Well, what can we say about all the points where x squared plus y minus 1 squared equals 0? Because they're both squared, both of these terms have to be greater than or equal to 0. When we add them up, we have to end up with something greater than or equal to 0. Yeah, that's true. Okay, so what does that lead us to? Well, the only way we can get 0 is if both of these were 0 to begin with, which means we need x to be 0 and y equal to 1. In other words, it's a single point. Just one point. So our level curve matches at just a single value. Wow. And similar down here. Okay, now you might be saying, well, what is that really telling us? What's actually happening is it turns out that this function, we haven't proven it yet, but eventually we'll be able to, the highest it can ever get to is 2. And the lowest it can ever get to is negative 2. So the function is bounded between negative 2 and positive 2. And so we're really seeing sort of a peak here. And if you think about what's going on, so this is our peak here at 2, and then here is at 1, here is at 0, minus 1, and minus 2. You could imagine what some other curves would look like. So for example, if you did a half, it would be a circle that you'd expect would look like that. And as you got closer to 0, the circles would get bigger and bigger. And of course, if you were between 1 and 2, the circles would start to sort of zoom in on that point there. So there we go. That's our level curves. Good. Good. Well, let's do another problem. Okay. Describe the domain of the following function. It's kind of like the ones we just did, except, it's a function of 3 variables. So instead of having just 2 variables, we'll have 3. So we don't necessarily have to sketch it because it's going to be a 3-dimensional space, but maybe we can get a vague sketch going. So we have a couple of things. We see a square root, a log, and a division. So we say, well, let's talk about our log. Here we say we need to have z be positive, because wherever we plug into our log has to be positive. And we need log of z not equal to 0. Well, that's the same as saying z can't be 1, because when z is 1, then you'd have log of 1 downstairs, and that's a division by 0. Okay, so that takes care of our log and our division. Let's turn to our square root. So for our square root, we say, hey, look, we need the inside. We need to make sure that that's positive. So that says 1 minus x squared minus y squared minus z squared has to be greater than or equal to 0, or x squared plus y squared plus z squared is less than or equal to 1. And we say, wait a second, we recognize that. X squared plus y squared plus z squared equals 1 is a unit sphere. The less than or equal says we're on the inside. So we're inside the unit sphere. And now we're starting to see, okay, all right. So we can say, look, we'll put it all together. We say we want all the points with x squared plus y squared plus z squared less than or equal to 1. And we say, well, look, we need z to be positive and z not equal to 1. Well, if you think about the sphere, the highest point it could ever be in the unit sphere is 1. And so we can say, look, and 0 less than z less than 1. So that's a description in terms of inequality. If we wanted to sketch a picture, it's a little bit hard to sketch in 3 dimensions, but we can vaguely talk about it. All right, we could do that. We would say, well, we have the bottom part, which is our z equals 0. So the bottom here, and we'll just do a little dotted. Okay. Don't include the bottom. That's our little side note here. But other than that, we do have the sphere coming up. All right, so we'll just make it look somewhat sphere-like as we come along. So the other thing is we don't include this one point at the very tippy top. So we don't include the point 0, 0, 1. Now you might say, well, Steve, wait, when you plug in 0, 0, 1, yeah, sure you get a 0 downstairs, but you also get a 0 upstairs, right? 0 over 0, that's okay, right? No, come on. We would never do that. Once you have divided by 0, forget it. All bets are off. Okay, so it's the top half of a sphere. Just knock off that top point, knock off that bottom surface, and you're good to go. That's our domain. Okay, well, one more problem. All right. Find and sketch some level surfaces for this function z minus x squared minus y squared. So again, it's similar before, but instead of level curves, it's level surfaces. And so it doesn't say which ones we have to do, and it doesn't say how many. So it's kind of a very vague question. But isn't that great? It means whatever we do, we got to be right. We have to do at least 2, because it says some, so that means more than 1. Let's do 3. So let's look at our surfaces corresponding to -1, 0, and +1. All right, so what would happen? So for -1, we'd have -1 would be equal to z minus x squared minus y squared, or what does that become? That says z equals x squared plus y squared minus 1. Whoop, z. For 0, we get 0 equals z minus x squared minus y squared, or z equals x squared plus y squared. And for 1, 1 equals z minus x squared minus y squared, or z equals x squared plus y squared plus 1. We say, well, look, it's really z equals, so that's good. And z equals x squared plus y squared, that's one we actually know about. Because we've talked about it when we talked about quadric surfaces. It's our bowl. So it's a bowl, and now we just have to think about, well, what are these doing here, the -1, +1? Well, they are shifts. So what we have is the following. So if here's our grid, so z equals x squared plus y squared is a bowl. So this would correspond to 0. And now z equals x squared plus y squared plus 1. Now that's a bowl that's shifted up. But you just move it straight up by 1. All right, good. And one more, the -1, well, that's a shift down. You see, the reason it's a shift down, there we go, is we're just affecting the z-coordinate by moving everything down by 1. So what are we forming? Well, what we're forming is kind of like a big infinite stack of, like, if you ever use like Tupperware, where you have nested Tupperware and you have it all nicely stacked one inside of another, and we get that shape. So there's a sketch of some level surfaces. Now, generally speaking, drawing surfaces is not very easy, so we're not going to do it very much. But we are going to talk about the idea of level surfaces. So it's the concept that's important. So when we talk about level surfaces, it's a function equals some constant. And from there, we're often good enough to make progress in what we're doing. All right, well, that's it for now. Thank you for coming for the practice. See you again in another session. Bye.